I'm Marc Miller, Senior Director of Marketing at Tabula. I'd like to talk today about morphing technology and business models at 100 gigabit per second and beyond. Before I do that, I'd like to talk about morphing technology and business models at 100 miles per hour and beyond. Both the automotive industry and the electronics industry, the semiconductor industry, are mature, established industries. It's notoriously difficult to start new companies when you're in an established industry. Most people wouldn't try to do that. Most business advisors would say you don't want to do that. Semiconductor industry is over 40 years old at this time. It's hard to start a new chip company. However, in the case of the automotive industry, which is even older, of course, over 100 years old, we've had a very successful entrant this year. That entrant is Tesla. They have a remarkable new car, and they've rethought the automobile completely in more ways than we might have imagined. They've been reviewed by Consumer Reports magazine, and they were described as the best car that had ever been driven by that crew. They did that by rethinking every aspect of the car and the sales experience. CNN described them as brimming with innovation. There are really three steps to this. I'm really looking at what can we learn from Tesla breaking into the automotive industry for us to create new companies that break into the semiconductor industry. First of all, of course, electric technology. Use 7,000 lithium-ion batteries stacked up. They're basically notebook batteries from Panasonic, and they have that electric system. Perhaps a little more surprising is they have a programmable platform. If you go in to buy a Tesla and you talk to one of their salespeople, they'll describe it as an iPhone on wheels or an iPad on wheels. Everything about it is programmable. The suspension, the drivetrain, the media, the works. There's nothing that you can't change on what effectively looks like an iPad on their dashboard. The sales experience is completely different. When you're working with their salespeople, they're actually directly employees. They have a T for Tesla. They're direct employees of Tesla in their stores. They don't call them dealers, they call them stores. They're not on commission. You can buy that car over the internet, or you can buy it from them at the store. They're at a fixed price. There's no dealing about the price. Everything is very comfortable. And I don't know about Europe, but I'll say for the North America, that normally when you buy a car, it's a very unpleasant experience, particularly with the business managers and the financial managers. The established companies can't seem to help themselves from creating an unsuccessful experience from the buyer's viewpoint. So this is a big difference. This cooperative business model is not something we've seen before in North America, at least, in car sales. So really, there's a triad of differences here in terms of how they've broken into the industry. It's not just one thing. And if you talk to anybody that has one of these cars, they love them. They've translated that into business success. It may not be as apparent here in Europe, but it's apparent in North America, and I'll tell you it's certainly apparent in Silicon Valley. They're selling a lot of these cars. In fact, in North America, Q1 this year, they sold more of these cars than the top German sedans in the same price class. I'd like to step back from this and then say, what can we learn from this success that they've had? Tesla is actually profitable at this point, surprise to everybody. So what can we learn from this and apply it to the semiconductor industry, this triad? Look back on that and apply it to our industry. Now, our industry, of course, is brimming with innovation as well. It's unbelievable the amount of changes that are taking place. It's a fun place to be. If you look at Gigabit Ethernet, for example, and I'm going to talk infrastructure, not the consumer side, but the infrastructure side. If you look at the infrastructure side, it took us forever, it seemed, to get from 1 gigabit per second to 10 gigabits per second with Gigabit Ethernet. There are a number of technological, mostly economic reasons for that, but it was a long time coming. Well, it ain't a long time coming for 40 gig and 100 gig. Those of us involved in that is happening faster than we can ever imagine. Some of us that bet on it a few years ago are really actually surprised at how fast things are taking off now. And we're not talking about a few 100 gig links that are used by Alcatel-Lucent, for transoceanic or transcontinental links, which used to be the way the first top speed came into being. Everything now is being driven by the data center. It's 100 gig in the data center going down. It's 100 gig between the data centers. We're just seeing it proliferate at an unexpected rate. It's really happening a lot quicker than we'd anticipated, in a broader sweep than we'd anticipated. Other things are changing too. The very fundamental computing model that we live with, that we've lived with for many years, the long, tumultuous, sometimes unhappy marriage between the client and the server on our desktop has led finally to divorce. The applications and the data have moved to the cloud. Very fundamental change. What I'm speaking about here are compounded changes. It's not just one thing changing. We have compounded changes in the infrastructure industry, and the industry has to deal with that. We don't know what's coming next. We have to be very flexible in terms of responding to that. Of course, once everything's in the cloud, as we well know, things are not all rosy there. From a security viewpoint, looking back, we ran McAfee or we ran Norton on our PCs, and that was about the end of it. Well, it isn't about the end of it anymore. We're in an era of cyber warfare. We have hackers, terrorists, even countries, as we're so familiar with now, attacking one another. And a single breach of security can mean 1 million credit cards lost in a snap of a finger. And I have a friend who had their identity stolen recently. It's an absolute nightmare. Any one of these things on an individual or a country's basis is really a nightmare. So we have to deal with this. If you look at this from a technological viewpoint, now we're talking 100 gigabit per Ethernet coming into the data centers and through the data centers. What's the upshot from a technical view of the cybersecurity? It means that if you're a firewall, you're not just handling 1 or 2 packets to know where to steer within the data center, the packet. You have to reach deep in the packet. You have to hit it multiple times. What is it? Is it safe? You have to check the header. You have to check the VPN connection. You have to check the data. So you have to go through that. You can easily have a dozen hits, a dozen times you got to touch the packet. So now you're 100 gigabit per second and you're touching the packet dozens of times. It is a problem that is, frankly, I think we're all aware of it, is not solved. If you look at the very best firewalls right now, they can't progress, they can't go through the data at nearly the rate that it's coming in. If you look at the data rates at which they're actually shielding, they're really looking through everything, it's much, much lower than this. So it's an unsolved problem that our industry has to face. And again, we're talking about compounding problems. These aren't the only problems or the only changes. There's a lot more going on. There's new leadership. There's been a total change in leadership of the electronics industry. Google, I'm not putting Google up here again. I'm not talking about search, that we're doing on our notebooks or our iPads. I'm talking about Google as a leader in driving changes in in the superstructure, the infrastructure. So Google, it's all Montessori. Nothing existed before we showed up. Let's think up everything from scratch and what we think is logically correct. It's just, it's a great model for insightful thinking and for taking things from scratch. And in terms of looking at the data center, they looked down at the data center. First they said, let's have warehouse data centers, of course, right? So it's a world of warehouse data centers. Then they looked within the data center and they said, well, wait a minute. I've got all these servers here, and I've got now these routers within my data center. They're kind of seeing there's dozens and hundreds of them at 20K a throw, which have a lot of work done, again now, if you will, to marry the control plane and the data plane. So with the Montessori vision, they look at it and say, heck with that, we're going to rip it apart. And in concert with Stanford and other universities internationally, the software-defined networks came into being. Google says, we're not only going to define it, we're going to build it. They build their own equipment. They put it in their data centers. They use it to communicate between data centers. SDN takes off, and it's the rage in the industry right now. And it's not only Google in terms of new leadership. And again, I'm not talking about our experience as consumers. I'm talking about the infrastructure. The compounding of change, the number of things that are new, the number of things we have to deal with here. Facebook, similarly, again, with new eyes, doesn't matter who came before, who cares, takes a look at the servers in the data center, and what are they doing? Are they doing super complex operations in general, each one of those servers? No, the reality is it's more mundane, right? We make a request, we want to search, or we want to have a Facebook friend, or whatever we're doing at that moment. It comes in, it's a query. You want to go into the database, you want to find that. It could be text, it could be an image, it could be video. You want to find it. You want to go east-west across the data center, make your associations. It's all about memory, it's all about association, and you want to fire it back. Well, let me see if I'm looking at that anew. Do I want a $1,000 processor for every one of those nodes, or would I like a $10 processor? Well, I think I'd like a $10 processor. And whereas Google is a little bit secretive about their approach to things, Facebook isn't. They created Open Compute. The spec is out there. Any one of us can go and take a look, and people are taking a look at how we're going to employ the data center and can bid on that for Facebook and spread that across the industry. So the result of that is now Google created the warehouse data centers, and then Facebook came and blew the doors off the data center and opened the door to the ARM SoC onslaught. The thread was picked up by the service providers. It's not limited to the data centers. The data centers are the drive, but it's not limited to the data centers. The thread is picked up by the service providers. They define their own standard. A lot of this was done in Europe. Network function virtualization. And again, they propagate these kind of changes to every nook and corner in the internet. So in sum total, in terms of what does the industry, the semiconductor industry, have to deal with in terms of flexibility, you start compounding this, 100 gig times different computing model, the separation of the server and the client, times cyber attack, times new leaders. How much more change can you have? You've got, in terms of SDN, you're rewriting the headers. The very packet header itself is now being redefined, and it's not complete. And nobody knows what it's going to be in 3 years. Even the people doing SDN equipment can't say for sure. They know the search header has gone from 320 to 640 bits for the TCAMs, but nobody knows for sure what it's going to look like. So from this level, if we look down from the cloud, if you will, there's an incredible need, more than ever in the industry, for flexibility. The ability to change, rapid time to market with a totally different product. Nobody knows what's happening. You better be agile out there in terms of infrastructure. I'd like to now come down from the cloud and come back to perhaps our more mundane world of semiconductors, and how has that long-established, mature industry dealt with these changes? Some places it's been good, some places not so. Looking at the semiconductor industry, last year, 2012, it was a $299 billion industry. Let's call it $300 billion. Of that, $100 billion or so is the logic part of it, mostly where we live, right? Logic part of that. Of the $100 billion logic part of it, 95% of it is standard cell. 95% is standard cell. Only 5% is programmable logic, FPGAs. And that seems like kind of a contradiction. We just went on a bit here about how important it was to be flexible. There's nothing more flexible than programmable logic, but it's only 5% of the market. And if you look back, programmable logic was invented by Freeman in 1984, and that's when Xilinx was launched, and Altera the year after. At that time, it wasn't too long after that they said, we're going to take a huge slice out of the logic pie. And the reality is it just hasn't happened. They've fallen way short. For all the goodness that they've done, for all the quality of the companies and the engineers, for all the people that are there, they haven't done that. It's only about 5% after all this time to today. It's not changing that much. So I'd like to dig in then, kind of stick around more in our realm here in terms of, let's look at that and why has that happened? I call it the logic paradox, and bear with me on this, a couple steps to it. The logic paradox is that while standard cells are by themselves inflexible, that being when you do your ST design or your Intel design, and you build your chip, you cast it in silicon, it's inflexible. You have to live with what you did. You can't change it. So where standard cells are inherently inflexible, the business models have been very dynamic. They have responded to the changes that we're familiar with. There were a lot of companies out there that changed with it, and again, we had new leadership, but the proper new leadership happened. So in terms of all the design that we know you have to do, but we're all only too familiar with the fact that I was using 100 million, not 200 million, but that the NREs are just sky high, and the time to market for an ASIC has gone out to a couple of years. So the number of ASIC vendors, or number of ASIC design starts dropped from 8,000 to about 2,000. I'll know that. The number of ASIC vendors dropped in a similar fashion. But the industry responded. It wasn't that there was the technological change drove a business change. So the center of gravity, the center of power, the center of revenue, the superpowers really in networking today are the Broadcoms and the Qualcomms. If you really look at who runs the show, I don't care what level you're talking about, they run the show. Because they were dynamic, they provided pre-engineered solutions, ASSPs, application-specific standard products. They just moved with it, and they were where people needed to be. Of course, with an ASSP, there's no NRE, and there's virtually no time to market. You drop it in place. So it was a very good response. But there's one price to pay. Of course, if you're doing a standard product, it's standard, and they're all the same. So there's no differentiation, and there's very limited flexibility. And this has had a profound effect on the electronic industry, and it's part of why Qualcomm and Broadcom are so powerful today. So the systems industry at large, and I'll come back to that, would really like the flexibility we talk about driven by the changes in our society and our technology today. So coming back to the PLD or FPGA side, that was fine in terms of when you do an FPGA, the designer has to do even a little bit more than people used to do with ASICs, in the sense that you have to do place and route for yourself rather than the ASIC company do it. That was fine when you were talking about a 10,000 gate design, 10,000 gate equivalent. It's not fine when you're talking about 10 million or 20 million or 30 million gate equivalents and trying to do that design. And the fact of the matter is that Moore's law has taken us up to bigger and bigger, higher and higher capacity of logic in programmable logic. It's quite astounding today. The simple fact of the matter is the tools haven't even remotely kept up. And I would even say we as a group here, in terms of providing complete IP subsystems, haven't kept up with the needs of the programmable logic. So the upshot of that is that in terms of a pre-engineered solution in programmable logic, it's programmable underneath, but as a customer, as a Cisco or an Ericsson, a Huawei, I buy it as if it's an ASSP. Either the programmable logic company has finished it, or they partnered with one of the companies here, or similar companies, and delivered that complete product. That has happened very little. There's, in the very low end, Microsemi has a model, I think somewhat like what I'm talking about, for their real low end parts that they're doing. It's happened very rarely in high-end networking that we're talking. In fact, it's hard to name a case where it's happened. So I consider there's this drive for flexibility, and there's more or less a vacuum up there in the ability of the industry at large to buy pre-engineered programmable logic solutions. So in terms of looking at that, I want to cast back our eyes for a moment to Tesla, think about the triad they had, and then see how that applies as it moves forward. At this point, I'm going to shift a little bit. I'm going to talk about our company's, Tabula's approach to this, and how we're approaching the triad. Others are taking it in a somewhat different fashion. I think we're doing it in a more of a gestalt, more of a complete fashion of embracing this triad of changes. First of all, you need a breakthrough technology. We have an underlying programmable logic technology we call space-time. Second of all, you need a programmable platform. We have an application-specific programmable device. Not just a programmable device, but one that's application-specific. I'll show you the application and how that fits in a moment. And that's a change. And then we have a cooperative business model we call the ASAP business model. And that's an attempt to reach out to soft IP providers and others in the industry and to provide that complete solution. And I will say, when we're talking about a disruption, it really is a disruption. It hasn't happened yet. There's a need. It's not easy. It's hard to do that. But this is what we're trying to accomplish. In terms of that application-specific device, the device itself, we are oriented towards high-end networking. That's our job in life, to deliver solutions to really tough networking problems. Our device has 23 megabytes of memory. It's unheard of in programmable logic. It's what high-end networking needs because you have to store the packets as they come in. You have to process them. You have to search in them and move them on their way. It's always been needed, but it hasn't been provided. We have a plethora of 40 gigabit per second, 100 gigabit per second Ethernet max media access controllers, some of the hard IP that goes with it. And the whole ensemble can run at 2 gigahertz, which is a higher rate of speed than is usually done in this industry. In fact, it's far beyond what's previously been done. In terms of those pre-engineered solutions, I said the goal of this was to provide a pre-engineered solution. At Tabula, we have about 20 system and apps engineers that are completely oriented towards high-end networking. So we can do quite a bit. We do quite a bit of IP development ourselves, soft IP on top of the platform. Then we reach out to partners, and I'll show you some of those partners in a moment, to complete the work. We have reference designs that are nearly complete, about the 80% point. When we approach customers now, we don't say, here's some bricks, you build the wall. We say, the wall is almost finished, and we will finish it for you, and we'll do the customization the customer asks for. I'll give you an example in a second. The other case we have, and I think this is more distinct, we are just starting to build up a library of parts, so we have ASSPs. We call them ASAPs, application-specific AVAX products. We are building up a library, just starting now, but we're building up a library of ASAPs so we can sell those as complete solutions to the communications customer base. And finally, kind of coming back again, finishing the loop, after all, these devices are programmable underneath, and even if we're selling it as an ASAP, and if a customer wants to add another feature, 1588 timing, or an extra depth in VPN, we can do that with a customization as well. Here's a couple of examples. This is that first example where we finish by customization. So we start with a reference design. We do some customization. We call it design to order. In this example here, just to get the gist of it, this is a 3 times 100 gigabit per second to 100 gigabit per second bridge. Okay, rarely, something that's beyond anything else that can be done in programmable logic at this point, but we can do it. It uses our 100 gigabit Ethernet max, so 400 gigabit Ethernet max, which would be, untold logic, but that's done in hard IP. And then we have all the wrappers and everything to go around that. In addition, we have the steering logic here. So the point here is kind of that things are at 100 gig, and it's tuned for 100 gig. We can handle, part of it is getting it in, part of it's being able to route the streams. 100 gig's pretty hard to route. It gets pretty wide in the chip at chip speeds. One more example. This is an example of a complete product that you'll be able to buy off the shelf as a device or as a board. We're working with our partner Algo Logic, and anytime you go very far in trying to do a complete networking solution, you need to provide layer 2 and layer 3 switch. That is exact match and associative match. And as ST Preventer was referring to the TCAMs, it's an essential part of it. In this case, it's done algorithmically and then gets down to all those memories I talked about and all the memory bandwidth to finish things off. So this is a complete 4x40 router or load balancer. Okay. When I was here a year ago, I did talk about Algo Logic, the partner that we have, and that we were developing these ASAPs with them as they were our first partner. At the same time, I identified that was covering layer 2 and layer 3 very well in networking, but that leaves layer 4 through 7. And we're talking about cyber warfare, content analysis, that's where the action is, layer 4 through 7. Layer 2 through 3 are the basics, but then you got to go into you're looking deeper. So we identified a need at that time for regular expression matching to go into firewalls. So I'm happy to announce today, and this is the first day that we've announced this, I'm happy to announce today that Tabula has a partnership with Titan IC Systems of Belfast, Northern Ireland. They're worldwide leaders in regular expression matching. And we have a good partnership, a good synergy between the companies. The regular expression matching is, it's just what it sounds like. It's, looking for a sequence of letters and numbers, any combination, any number of times. It's complex. It's fundamentally complex. It doesn't really easily map to any kind of standard architectures. It does map well to ours. That Titan IC Systems has NFA algorithms that are memory-centric. So they're memory-centric. And, of course, our space-time architecture is memory-centric. It works well together. You have the capacity and the bandwidth, the number of ports to handle it. And this is the block diagram of their IP and some of the collateral we're developing with it. Looking forward this year in terms of where we'd like to expand, in the coming year, we'd like to expand into big data, data analytics. Again, if you kind of think in terms of the memory-oriented, that's kind of an extension in terms of memory orientation, memory search processing. A lot of big data is using Hadoop and regex for big data searches, so it's a natural extension for us that we'd like to accomplish, extending our partnerships and cooperation in the industry next year. And then towards the end of the year, we're going to be looking into signal processing, and we may be concentrating on multi-gigabit per second RF direct sampling. If you kind of follow the thread for our company, we're at the high end. In the industry we appear in, we'll be at the high end. So in summary, we had a little fun, at least for myself, in looking at Tesla and how they managed, surprisingly, to break into the automotive industry, and they received a lot of kudos for that. We're doing pretty well ourselves in terms of the attention that we're attracting. What we'd like to do is take a combination of the new technology, the new application-specific programmable device, a new cooperative business model to reach out and solve that tough problem of working together with, cooperating with companies in the industry to provide complete pre-engineered solutions to the system companies for the toughest communication problems that are coming up in the next few years ahead of us. Thanks.